So, hey everyone, I'm Aryan, and today I'll be talking about the Schrodinger wave equation and its types. Today's discussion will be purely based on two dimensions. I'll not go into the three-dimensional wave equation. We'll keep that for another video. So, first of all, we have the most basic form of the wave equation. I h cross dou psi over dou t equal to Hamiltonian of psi. Yeah. So now this psi is what we call the wave function. And the h is what the thing which is written as h is called as the Hamiltonian. It is something which we determine by putting in some other values. We'll see that later. So this is basically a linear differential equation. So I'll show why I'm saying it's a linear differential equation. So the h cross basically is the reduced Planck's constant, which is basically the original Planck's constant, which is 6.626 into 10 power minus 34 divided by 2 pi. Yeah, so the h is the Hamiltonian. This is the reduced Planck's constant h over 2 pi. Now this I is the iota or root under minus 1. Yeah, so this is basically the basic form of the wave equation. Yeah, so let us write in this form. Yeah, so this is why I said this was a linear differential equation. This is a Hamiltonian. Now, speaking of operators, operators are something which we use to operate on the function, on the required function or the variable. Here we have it as psi or the wave function. Now, operators are analogous to matrices. So in matrices, we have vectors, and in operators, we have the analogs like eigenvalues and eigenstates, eigenstates in operators and eigenvalues in vectors. So yeah, so I hope this part was clear. Now, yeah, so we can use the idea of eigenvalues here. So I can write this. So this is how we denote the eigenvalues. We can refer the linear algebra part for this. I'll not dive into detail here. Now the A here, capital A, is the operator, similar to the Hamiltonian, which we have in the basic form of the Schrodinger wave equation. Now we have different waveforms like the sinusoidal wave here. Now when the sign between k and omega is minus, that means the wave is traversing in the positive x direction because yeah, and if the sign between them is positive, we have the wave propagating in the negative x direction. If it were ky, then the wave would be moving in the y direction, positive and minus according to the sign, and same for z. We also have the cosine wave, similar. Now we also have two different types of wave, which is the exponential types. These are the types. Now we add them up, the waves in the two different directions, and we get these two to satisfy whatever we need. So we write psi of as a function of position and time as this. Now we have momentum as h cross times k and E has h cross times omega. One thing to note here is that, yeah, this is a wave function. So one thing to note here as the units of the Planck's constant is the same as angular momentum, just as a side note. How? So if we write something of this sort, yeah, so here we see that the momentum operator can be written as h over I dou by dou x. This is what we call as the momentum operator. Now, psi of x comma t, I write it as this. Now, since this is a function in two variables, we are using partial differentials. So the derivative with respect to time is minus of I omega. We need to use this in a future result. Use this result in the future. So yeah, moving on. This was the form. Sorry. So now here, after the derivative of d psi over dt here is minus of I omega. Just put it here. So we know that h cross omega is the energy. Now E equal to p square over 2m for non-relativistic. Yeah, just let me change. Yeah, p E equal to p square over 2m when it comes to non-relativistic mechanics. We are going to use this formula many times. Now E psi equal to theta psi, because we are trying to find the energy operator here. Now theta is something for us to invent or to find. We need to find theta. Now put E equal to p square over 2m. So E psi equal to p square over 2m psi. Yeah. Now I'll take one p inside. So p over 2m into p psi. Now instead of p, I'll be placing the value of the momentum operator here. Yeah. So p over 2m. I just place the value here to by to x psi. So I take the p inside the derivative p of psi. Now again, I put the value of p, the momentum operator here. So 1 over 2m h cross by I, dou by dou x, h cross by I, dou over dou x psi. Therefore, now I'll just rearrange them. So this is what we get as the energy operator. So the energy operator E psi equal to minus h square by 2m dou square by 2x square psi. So the product of the two i's, I square equal to minus 1, hence the minus. So we also see that psi is a complex number. That is because here this part, the part on the left hand side is complex because of the iota. And if psi is real, we get something of the sort of complex equal to real, which is definitely not correct here. So psi has to be a complex number. Just a side note. So we have the values of the momentum and the energy operator. Let's just write it here. Yeah, so this is the momentum operator, h square over 2m dou square by 2x square. This is the energy operator. So we have the momentum as well as the energy operator now. Now we proceed to writing the next form of Schrodinger wave equation. Yeah, so this was the original. So psi is an energy eigenstate because these are operators and not matrices. Or we can also say it is a state of definite energy when this holds true. Okay, so moving on. E equal to p square by 2m again. So here I'm just p into p. I'm just trying to get a relation between the energy and the momentum operators now. Minuses cancel out. Now I rewrite the Schrodinger equation like this. So this form of Schrodinger wave equation is known as the free particle Schrodinger equation. So this is the energy operator, minus h square by 2m dou square by dou x square is the energy operator, which also turns out to be the Hamiltonian. So from this we can also say that, yeah, so from here we can make out that the Hamiltonian is the same as the energy operator here. So we have two different relations here. The first is the relation between the Hamiltonian and the energy operator, and we also place the value of the energy operator in the equation to get the free particle Schrodinger equation. moving on. So we can also write this as this, since Hamiltonian and the energy operator are the same. Now, the next type of Schrodinger wave equation is that we assume that the particle is placed in a potential. So how do we write this potential? We write it as V of x comma t. Now we know that total energy equal to the kinetic plus the potential energy. Now the E total is denoted by the energy operator, which is also the same as the Hamiltonian. So P square over 2m is the kinetic, corresponds to the kinetic energy here, and the potential is written as this V of x comma t. Now we place this whole thing of as the value of energy operator in the equation. So we get the complete Schrodinger wave equation in 2 dimensions. Yeah. So this is basically the Hamiltonian, which is equal to the energy operator. This is an operator, even this is an operator. So, but the potential is a simpler operator as compared to the kinetic energy operator. So the main takeaway here is that V of x comma t is also thought as an operator. All right, so that basically concludes the different types of Schrodinger equations in 2 dimensions. I'm not considering the 3 dimensions here. So this is basically the complete Schrodinger equation. Now let us summarize. So the first is the basic form of the Schrodinger equation, which we started off with and developed. Yeah. So this is the basic Schrodinger equation. We also said that it is a linear differential equation. Now we looked at the basics of some linear algebra, like eigenvalues and eigenstates. Now these are the different types of waves which we basically we added them up to see if we get the desired result or not. Now momentum operator, energy operator, these are the values which we got. Now we also have the free particle Schrodinger equation, which we found out. We also got this equation, we also got this relation, the Hamiltonian is equal to the energy operator. So I'll just remove this. Yeah. Now we also saw what happens when the particle is put in a potential. So we equated the total energy as kinetic and potential. We used V of x comma t as the potential energy, and we got the complete Schrodinger equation in 2 dimensions. So we used this Hamiltonian equal to energy operator, and we placed it in place of the Hamiltonian. So basically, this is the kinetic energy, and yeah, so we got the Schrodinger equation, and the final takeaway is that V of x comma t is thought as an operator. So yeah, that's it, guys. Thank you for watching, and see you next time. Till then, bye bye, and thank you.